Good morning everyone, I'm FENGHAN, and today I'll be sharing my research on how to use machine learning to improve operational efficiency in cross-border e-commerce. The full title is Cross-Border E-commerce Operational Efficiency Optimization Analysis based on machine learning. Here's the flow of today's presentation. I'll briefly work through the background and why this topic matters. Then talk about the data and methods I used, the models I built, and finally, the key results and what they mean in practice. Let's begin with the background. Cross-border e-commerce is expanding rapidly, with global online sales projected to exceed $80 trillion by 2027, and small sellers face issues like non-fulfillment times, poor inventory turnover, and high return rates. This problem isn't just operational, it affects the entire customer experience. Native deliveries or stock-out damaging platform reputation and increased customer churn. Platforms like Amazon also risk increased costs from returns and complaints. So understanding what causes low efficiency isn't just helpful. It's critical for maintaining service quality in a highly competitive market. The study focuses on two main goals. First, to predict operational efficiency using machine learning, and second, to identify key influencing factors behind it. To guide the research framework, I drew upon four key theories. This research is built on four key concepts: resource allocation, using inventory and capital wisely, dynamic management, being flexible when things change, value chain theory, coordinating all parts of the operation, and the smile curve, which reminds us value comes not just from making products, but from branding and logistics. These ideas help shape the way I selected variables and built the models. Next, let's take a look at the data. The data comes from Amazon FBA from April to June 2025, a busy period. There are 857 order records, each with 9 cover variables. Things like fulfillment time, refund status, return reason, inventory health, customer feedback length. The key innovation is the construction of an efficiency score. This is a composite metric ranging from 0 to 100, combining delivery time, refund news, and customer experience signals, rather than relying on binary outcomes like returned or not. The score offers a more continuous, interpretable performance indicator. Before modeling, I cleaned the data, removed variables with over 90% missing, filled key missing values like shipping time using the module, handled outliers with the IQR method, included category variables like return reasons, and split the data 17% for training, 13% for testing. Also, I checked for multicollinearity, no strong correlation between features. Besides cleaning, I also explored some patterns in the data. Then I did some quick exploration. Most orders were priced between $10 and $13. Refunds were heavily skewed. Just a few orders caused mostly refund losses, and when fulfillment time passed 20 days, efficiency scores dropped fast. So, timely shipping and smart inventory clearly matter. I built 3 models: XGBoost, CanBoost, Random Forest. They are ensemble models, good for structured data and explainable. I turned parameters with grid search and use earning stopping to avoid overfitting. Let's look at how they performed. CanBoost had the highest R-square 0.936 and it overfit the training set only2. XGBoost had slightly lower R-square 0.928 but more stable performance and lower error. So I picked XGBoost as the final model. Random Forest has the lowest performance, especially in generalization. XGBoost predictions align closely with actual efficiency scores. It used k-means clustering to group signals into 3 types: high efficiency, low return rate, fast fulfillment; middle efficiency, average performance but inconsistent shipment timing; low efficiency, frequent delay and high refund loss. This clustering platform allows to personalize signal support. For example, high-efficiency signals might receive priority warehousing, while low-efficiency ones may require intervention or penalties. A few key takeaways from the model. Inventory turnover was critical. However, higher turnover meant better scores. Fulfillment time had a strong negative effect. Delays hurt performance. Return reasons and customer feedback also had clear influence. In short, fast delivery and healthy stock management really meant for signal efficiency. Based on these findings, here are my suggestions for signals. Use predictive inventory tools. Ensure fulfillment is within 7 days. Analyze return feedback regularly. Heavily target strategies based on performance cluster. For platforms, offer localized or 3PL warehousing, building real-time efficiency dashboards. Set alerts for fulfillment delays. One possible real-world application is an automatic scoring system integrated into a single dashboard. This score could influence platform visibility, warehousing eligibility, or even commission rates, rewarding high-efficiency signals with better results. That's the end of my presentation. Thank you so much for your time and attention.